Dmitri Mendeleev is known as the father of the modern periodic table. He was a Russian chemist who lived mainly in the, as you see there, mainly in the 19th century. And what he was able to do was to systematically lay out the chemical elements based on properties. Now remember, in the time of Mendeleev, this was prior to quantum mechanics, prior to the understanding of the electronic structure of the atoms. We now will claim that the periodic table is correlated to electronic structure. Mendeleev correlated designed his periodic table correlated to chemical properties. Well, it turns out that the chemical properties come from the electronic structure, so it's not surprising that his periodic table follows the electronic structure even though he didn't know electronic structure. So in any event, prior to Mendeleev, it was noted, certainly they could determine that the relative masses of the elements. They knew how much hydrogen weighed compared to carbon, how much carbon weighed compared to gold, and so forth. They also noted that there were repeating patterns of physical and chemical properties that the elements exhibited. So every 8 elements or so, as you went up in atomic number for the elements and atomic mass for the elements, it seemed like the properties repeated themselves again. So there were many attempts made to lay out the various elements into an ordered, structured system where you could show this repeating pattern of behavior. Try as everybody at the time would, there didn't seem to be a consistent way to systematically lay out the elements into a repeating pattern or a periodic pattern of chemical properties that repeatedly came about as you increase the mass of the elements. So Mendeleev took a bold stroke. What he did was decided, well, the reason that the known elements don't fit a repeating pattern is that there's a few elements we don't know yet. If we knew these elements that I can predict should exist, then everything falls into place. So Mendeleev predicted the existence of 3 unknown elements. He predicted their physical properties, meaning how much they'd weigh, what their density would be, and things like that. He predicted their chemical properties, meaning how they would react with fluorine, how they would react with hydrogen. And when he did so, he laid out these 3 elements and put them into spots where they should go in the table. Then everything fell into order. There was a repeating pattern of behavior of the elements after he made these predictions. Subsequently, people looked around and found 3 new elements. Now, he didn't name them, or they were named by different people. They were gallium, germanium, and scandium, and they were found, and Mendeleev had left blanks in his table for where these should be located, and they fit exactly into the table, into the locations Mendeleev predicted, with the properties that Mendeleev predicted. So this was quite an achievement at the time. And remember, basically the idea was Mendeleev just thought outside the box. Well, the reason they're not fitting is we just don't have all the information yet. Other people were trying to take it as the fact that what they knew, the elements they knew at the time, were all the elements that existed. It was not ever guessed that there could possibly be any unknown elements. So we're going to spend essentially this entire lecture looking at the properties of the periodic table. By the time we're done here, we should have a very intimate knowledge of the connection between electronic structure and the layout of the periodic table. Of course, the periodic table is always presented in this ubiquitous form that you see on this particular slide. And it is laid out specifically by Mendeleev originally to mimic a pattern, to reveal a pattern of behavior chemically and physically of the elements. But now what we understand is that the chemical properties in particular are a function of where electrons are distributed on the atoms. So what we will then do as we now begin an investigation of this periodic table, let's look at the columns and rows of the table. The rows are called periods of the table. Elements in the same period have the vast majority of their electrons in the same principal quantum number. The electrons are filling the same energy level for the quantized discrete amounts of energy that the levels can possess when they're in the same row. Now the columns of the periodic table are known as groups, and elements in the same group have very similar chemical reactivity. Like for instance, they will form the same ratio and proportional combination when they combine with the same element. So for instance, if you take hydrogen, lithium, sodium, potassium, everybody in column 1, and combine them with fluorine, they will all make HF, LIF, NAF, KF, or they combine in a 1-to-1 ratio with fluorine. Whereas elements in column 2 will combine in a 1-to-2 ratio with fluorine. They would form BeF2, MgF2, CaF2, SrF2, and so forth. So the groups of the elements are grouped in that fashion because of their chemical similarity down the column. The elements listed in red on this version of the periodic table are the S block elements, meaning they are placing their outermost electron in an S orbital. Now remember, S orbitals begin on energy level 1 and then proceed downward. On every row of the periodic table is a new energy level. So row 2 is energy level 2, row 3 is energy level 3, and so forth. So the row 2 elements, lithium and beryllium, are putting their outermost electrons 2s1, 2s2. The elements sodium and magnesium are putting their outermost electrons 3s1, 3s2. Now helium is kind of in a weird situation. You'll notice where it is located in the table. Technically, it should be placed on the top of column 2 based on electronic structure. And in many periodic tables, there are 2 versions of helium, one on top of column 2 and then one on top of column 18, as seen here. The reason chemists prefer to put helium in column 18 is that its physical and chemical properties mimic those of all the other column 18 elements, the noble gases. They're all gaseous elements, whereas column 2 elements are all metals, and the column 2 elements are all highly unreactive. That's why they're known as the noble gases. And so helium, for chemical reasons, is placed in column 2 in column 18 instead of in column 2. It's pretty much the only case in the periodic table where we can make the claim that it's located in the wrong position. This slide shows the electronic structure of the first 4 group 1 elements: hydrogen, lithium, sodium, and potassium. Now what you should note is the way we're listing them here in the boxes next to the electron configurations. I'm showing the blue electrons being the core electrons, those in the completed shells or rows of the periodic table. So those would be, for lithium, you would put an He in place of the blue box. For sodium, you would put an Ne in place of that blue box. And for K, you would put an Ar in place of that blue box if you were writing abbreviated configurations. At the valence level, the red box electrons are showing the valence level electrons. You will note for hydrogen, it's placing its outermost electron 1s1, lithium 2s1, sodium 3s1, and potassium at energy level outermost electron 4s1. The boxes listed here in blue are known as the p block elements. The outermost valence electron of these elements are going sequentially into the 6 locations available for the 3 degenerate p orbitals that begin on energy level 2 and then continue on every energy level from 2 through, at least in this particular table, we have 2 through 6 for those various energy levels. This slide shows the first 4 group 13 elements: boron, aluminum, gallium, indium. Now, once again, we are listing blue electrons as core electrons, red electrons as valence electrons. What you will notice is that they start out pretty regular there, showing that boron and aluminum have valence level electrons 2s2, 2p1, or 3s2, 3p1, so they appear the same at the valence level. You should also note that boron and aluminum have the same Z effective. Z for boron is 5. If you subtract the 2 core electrons off, Z total is 5 total protons in the boron nucleus. Subtract off for the 2 core electrons, Z effective is 3 for the valence electrons. For aluminum, the total charge is 13, so Z is 13 on aluminum, and there are 10 core electrons for the 1s and the 2s and 2p levels, and so 13 minus 10 would give, again, a Z effective of 3 for aluminum. So the outermost electrons on aluminum see the same amount of charge as the outermost electrons on boron. Now things get weird with gallium and indium because now you have appearance of the D level. Notice I put the 3D as technically being core electrons. They're on energy level 3. So if you only count the red box level 4 electrons, notice that gallium also has 4 S2 filled and 4p1. So that's on level 4, again, 3 valence electrons similar to aluminum and boron. Same thing is true with indium. Its core electrons are listed in red, in blue, and the valence in red. And the 4D, even though it is on the outermost period in terms of location, its electrons on level 4 are technically core electrons. So this indium technically, again, has a Z effective of 3 and has as well 3 valence electrons, just like boron, gallium, and aluminum. So the chemical properties that result from these 3 valence electrons with the same core are very similar. Now at the bottom of the page, I'm showing how I would represent boron, aluminum, gallium, and indium using the abbreviated notation. And for those of you that are just starting doing this, maybe the best thing to do would be to write out the entire triangle, do the complete electronic structure, and then just eliminate out to the group 18 elements, which for helium would be the 1s2, and for neon, argon, and krypton would be 2p6 at the end, and then for the argon it would be 3p6 would be where you'd terminate the electronic structure, and for indium it'd be 4p6 where you would terminate and designate all electrons below that as being core electrons. This version of the periodic table has highlighted in green the so-called D electrons. Now remember, Ds first appear on energy level 3, but you will notice that these D electrons are being filled after level 4 electrons, which penetrate the shielding better than the Ds. They're getting filled after those 1 level higher electrons are getting placed before the inner level D electrons are getting placed. So beginning with column 3 through 12, we have 3D 10 for the row 4 elements, 4D10 in row 5, 5D10 in row 6, and 6D only goes out to 7 for the 7D elements. For the 6D elements, they only go 1 through 7 outward in the periodic table shown here. Now there are newer periodic tables with other elements as well. And the D shell is now actually completed with the newer periodic table. This slide shows the group 5 D block elements: vanadium, niobium, and tantalum. Notice again, if you wrote out the triangular form, you would write out and occupy with the Aufbau principle the lowest energy orbitals, and vanadium would end at 3d3, niobium 4d3, tantalum at 5d3. Now below each one I show, if you were going to write the abbreviated form showing all core electrons and then what is being filled past the core, I would have my argon with the 4s2 3d3, krypton 5s2 4d3, and xenon 6s2. Now it has the F that is beyond the outermost element of xenon, and then I have the 4f14 5d3. So all of these group 5 elements are placing outermost electron at a d3, and so again exhibit great chemical similarity. On this version of the periodic table, shown in yellow, are the F block elements. You will notice, not surprisingly, there are 14 boxes in each of the rows. And of course there are 14 boxes because if you're placing your outermost electron in F, there are 7 degenerate F orbitals, each that can be doubly occupied. So there's a total of 14 electrons that are represented. Now they're in a weird position on the table. Now remember, the deal is this: they are yanked out of the table in order to make the table fit into a landscape size printing. Really, they begin at element 58. So you notice the periodic table, the elements jump from lanthanum at 57 and jumps all the way to hafnium at 72. You should slide these elements in that particular row. And notice this is energy level 6. You've passed the 6s up before you begin to fill these F orbitals. The first available F orbital, according to quantum mechanics, is energy level 4. So this is really a 4F getting filled after the 6s. The 6s penetrates the core so effectively it can be lowered in energy below an energy level 4F orbital. That's pretty remarkable, and that's a pretty big testament to the strength of this penetration and energy lowering that s orbital electrons can experience. The 6s electrons get filled before level 4f electrons get filled. Pretty remarkable. Now again, the same thing is true for element 90, thorium. You'll notice in row 7 of the periodic table, it jumps from actinium to unyl quatrium, and there's a big jump in between there where you should slide these level 5f orbitals in the periodic table. That would, so after the 7s electrons are filled for francium and radium, then you come back and you place in these the 5f electrons after that. What you now should be thinking in terms of when you view the periodic table is this sort of structure. And I would expect that you know something about this when we have our little assessment upcoming. That when you see the rows of the table, the blocks of the section are such that on the left, the 2 blocks on the left are filling s orbital, the 6 blocks on the far right are filling the p. In the main block of the table, the 10 between the s and p are the location where d's are filled. Notice they are 1 row out of place because of the penetration of the level 4 and level 5, level 6, and level 7 s's below the level 3, 4, 5, and 6 d's. And also then you have finally pulled out of the table the 4f and 5f that are placing electrons 1 through 14. Those are actually 2 levels removed due to shielding and penetration. The 4f goes in at the same point after the 6s, the 5f goes in after the 7s, and are yanked out of the table for making it more aesthetic. Now again, you should again be able to recognize immediately this structure of the table based on what electron is being placed into what energy level for the outermost electron. So, for instance, if you were asked what is the position where the outermost electron for sulfur is being placed, well, you could write the triangle rule and put all the electrons in for the 16 electrons for sulfur and so forth. You could do all that and come to the conclusion where the last electron is. Or you could notice it's in the second p row down. That would be a 3p. It's the fourth box over. So the outermost electron on sulfur is a 3p4. Lead is also a p block element. It's element 82. And again, you could write out the 82 electrons in the Aufbau principle with the triangle rule and come to this conclusion. Or, based on your better knowledge of the periodic table, you note that the box for lead is in the p area. So you know it's got to be a p. You notice that it is the fifth p orbital down, but because p orbitals begin on level 2, it is the 6p orbital, and it is the second box over, so the outermost electron in lead must be a 6p2 electron. Strontium is element 38, and the location of strontium immediately tells you it's in group 2 element. So group 2 elements are all putting outermost electron in S, and S is beginning on energy level 1, and since strontium is in row 5 of the periodic table, this S electron that it's placing is a 5s. It's the second of the two in the S block, so the outermost electron on strontium is 5s2. Now again, if you complete the triangle and do all the things and you would come to this same conclusion. But now I want you to get used to just looking at the table and recognizing where the electron is going. Let's look at the case of silver. Silver is in the section of the table that we identify as the D block. It's in the second row of this D block. It's element 47. And being in the second row, remember, the 3D is filled first, the 4D is filled second, even though the 3Ds are placed in energy level row 4, and the 4Ds are placed in energy level row 5. So this will be a 4D, and I count over. The silver outermost electron would be a 4D9 electron. For the case of titanium, element 22, it is located again in the D section of the periodic table. It's in the first row of the D section, and the first available D orbital is the 3D. It is the second element into the D block of that row. So the outermost electron for titanium would be a 3D2 electron. Finally, let's look at the case of berkelium, one of the radioactive elements, very near the bottom of the table, element 97. It's unstable. The nucleus can't handle the 97 protons in the nucleus, so it's a radioactive element. Now, the location of berkelium is in the 14 block section, which represents the F outermost electrons are being placed. Remember, this is the second of the F blocks. The first of the F blocks in the first place the F is available is energy level 4. So this being the second available F orbital would be an energy level 5 F orbital. Now it is actually filled after the actinium element in row 7. So after the 7s level is complete, this 5f level is being filled. So there's a lot of weirdness going on in terms of the breakdown of the order of filling that we have due to the enhanced penetration of the s level electrons compared to the f. So this 5f orbital is getting filled after 7s, even though it's on 2 energy levels lower than level 7s. And I count the boxes over. Berkelium is the 8th box over. So being the second available f orbital, the outermost electron on berkelium must be a 5f8. Now what I would like to point out to you though is that if you were to do this using the triangle rule, what you would find is that the last electron of this 97 electrons on berkelium, according to the triangle rule, would be 5f9. So there's a discrepancy and a breakdown here in what the triangle rule says compared to what the location in the periodic table says. So let's not fret over this and let's not split hairs over this. I'm not going to ask you cases where if I want you to apply the triangle rule, you will apply the triangle rule and get the value that the triangle rules give you. I will try to avoid any of these complexities due to weird arising values based on a breakdown of those rules. Okay, so then based on your knowledge of the periodic table, you should be able to, I would hope, answer questions of these types on the following couple slides. Now, you can certainly expect to see questions of this type when we have our upcoming assessment. Now, the first one we'll pose is the question, what is the first atom in the periodic table to have 27p electrons? Now, there are several atoms that do have at least 27p electrons, but we're posing the question, which is the first to have 27p electrons? So what you would do is go to the p block and just begin to count up. Boron is the first element to have a p electron. So if the question said which is the first element to have a p electron, that would be boron. By the time you get across to neon, there's 6 p electrons total. By the time you get to argon, 12. Krypton, 18. And then by the time you get to xenon, there are a total of 24 p electrons because of the fact that you have 4 completed p orbitals. So when we go down to row 5, I need to add 3 more p electrons to that total. So I will come across tellurium, lead, and then I finally come to bismuth. Bismuth is the 3rd p electron element into the 5th p orbital, and it takes 4 complete orbitals plus 3 more to have 27 total p electrons. So bismuth is the first element in the periodic table that has 27 p electrons. Now every element after bismuth has at least 27 p electrons, and some of them have more. Of course, as a matter of fact, all of them have more than 27 p electrons. Okay, now the second question, B. What is the first atom in the periodic table to possess 5 filled s orbitals? So what you would do to answer this is turn to the s block. Of course, the first 2 rows of the periodic table represent the s block, and each row of the periodic table places 2 electrons in an s orbital. So in order to get to the 5th completed s orbital, I'd have to go down to row 5, and I look in row 5 at the second column element, and I see the row 5 second column element is strontium. So strontium is the first element in the periodic table to have 5 filled s orbitals. Every element after strontium has at least 5 filled s orbitals, and by the time you get down to cesium, you're beginning to put electrons into the 6th s orbital. Many elements exhibit magnetic properties, meaning they are either attracted by magnets or in some cases can be made into permanent magnets. And the nanoscopic property which determines whether or not elements can be made or be attracted to magnets, be repelled by magnets, or actually become magnets is due to their electrons. And as a matter of fact, due to how many kinds of unpaired electrons they have, according to the ideas of Hund's rule. Remember what Hund's rule says, that when you have electrons that are populating energy levels, they prefer to go into separate degenerate orbitals with matching spins first before they come back and begin to pair. If there's enough unpaired spin character, each of these little spins, due to its moving charge, is magnetic, and if enough of these unpaired spins align, the material can then be attracted by magnetic fields. And if there is enough of this unpaired magnetic characteristic, they can be made into permanently magnetic materials. So some materials will be only magnetic in the presence of a magnet. We call that paramagnetism. Others can be permanently magnetic. We call those ferromagnetism. We call that ferromagnetism. Now, in addition to that, we have something which we will call a diamagnetic element. A diamagnetic element are elements that are repelled by magnetic fields when they are placed in them. So what I show on this particular slide is the periodic table, and it has 4 different colored schemes to the boxes. If there is no color in the box, it is a non-magnetic element. If it is a yellow element, it's a diamagnetic element. If it's a blue element, it's paramagnetic, meaning it can be attracted by a magnet. And if it's a red element, and you see there's a handful of the red elements, they can be made into permanent magnets. Now, I don't expect you to memorize this table and regurgitate for me which element is permanently magnetic and which isn't. But what we are going to do is delve into reasons behind why particular elements are diamagnetic and other elements are paramagnetic or ferromagnetic. Let's first look at a diamagnetic element such as zinc. And I think it will become clear why zinc is diamagnetic. If you look at the electronic structure of zinc, first I show the abbreviated form of it. It has a core the same as argon. Then above argon, it has 4s2, 3d10. And if you populate the 4s2 and 3d10 electrons, you note that all spins are paired. So this has canceling spin magnetic moments, and so therefore does not exhibit magnetic attraction to a permanent magnet, or cannot be made permanently magnetic due to this lack of spin magnets. On the other hand, elements with unpaired spins can be induced by magnets to be attracted. If a element has the property that when you place it near a magnet, it can be attracted to the magnet, we call that paramagnetic. And the idea is that the unpaired spins on the element, the electrons on the element that is paramagnetic, when placed into the proximity of another magnet, these can all work together to be pulled towards the magnetic material. The electrons being fairly mobile in these materials, they kind of run around and line up so that the north pole of a permanent magnet will align with the south pole induced in the material as the little magnetic spin magnets move around in the material. And likewise, if you place a north pole near it, the south pole spin magnets will line up near the material and cause an attraction with the material. Now, a material such as iron, as the name kind of implies, is a ferromagnetic element, which ferro, of course, is some Latin term indicating iron as the material that demonstrates this type of property. A ferromagnetic material, and again, we saw previously there's only a handful of these, including nickel, cobalt, and neodymium, and I think dysprosium is another ferromagnetic element. These have plenty of unpaired spins available, and the unpaired spins that are available can now, through the action of just strong high magnetic field exposure, can be made to line up permanently so that these materials have a constant magnetic characteristic with them. So this is very important and has many applications in all sorts of electronics devices and other systems as well. Now what we're going to do is examine a series of trends of the elements towards various properties which we will later use to define them as we move towards putting them into combinations to make molecules and compounds. So what we need to do with regard to this is, when we're worrying about forming bulk samples of material, one of the driving forces is how the atoms pack relative to one another. So essentially, we are interested in how much volume atoms exclude, or how much space they take up when they pack together to make the various phases of matter. So one of the properties that is of great interest to chemists is what is known as the atomic radius. The atomic radius, as defined here, is the distance from the center of the nucleus to the edge of the outermost electron. Now, this gets a little bit dicey when we start to try to think about this. Of course, a radius is a ray that starts at a point and then goes outward in space from that point. So the point of starting of this is the center of the nucleus, and then we go outward from the nucleus, heading into the electron cloud surrounding the nucleus. And remember, technically speaking, in quantum mechanics, electrons are not particles. They have a probability density, or a mist of location likelihood, spread over the nucleus, where the electrons really have a wave-like character more than a normal particle-like character. So as I spread this wave-like character over the outer edge of the nucleus, and I look at where the clouds of electron likelihood end at the valence level. Remember, I would go to the outermost energy level, the last n value being populated. This would be where this atomic radius ends, and then I measure that distance, and then typically I should use, of course, for the SI world, the units of meters. Well, as you can well imagine, a meter is way too big of a unit to use to measure this distance from the center of the nucleus to the outermost edge of the electron density. As a matter of fact, I could use meters, but it would have 9 or 10 zeros along with those numbers measuring the distance outward. So what we typically do is scale the units in the metric form so that they fit better for discussion of atomic radius, and one of those would be nanometers. The typical size of atoms in nanometers is on the order of tens to hundreds of nanometers in size. Now, that's again one reason why visible light of wavelength hundreds of nanometers and UV light of wavelengths of hundreds of nanometers interact very effectively with the electrons that are acting like waves around the nucleus. They're on the same scale. Now, another familiar unit, at least used in chemistry and physics, that is really not technically an SI or a metric unit, is the unit known as the angstrom or angstrom, named after this Swedish physicist who looked at the size of the lattice of packing of atoms in a solid structure. And the angstrom, it turns out, is 10 to the minus 10 meters. So it fits kind of between the nanometer and the picometer. There are 10 angstroms in 1 nanometer. So a nanometer, remember, is 1 times 10 to the minus 9 meters. So a tenth of a nanometer is equal to 1 angstrom. So we would think of this scaled on the metric system in nanometers and in the physics scale system in angstroms, which are tenths of nanometers. So based on a cartoon showing what would happen as you go down a group or down a column of the periodic table, we would see trends such as you see with the red circles. The further down the column you get, the bigger the circle gets, or the furthest to the outermost regions of the electron density. So I'm not going to ask you anything weird diagonally or anything like that, but you should be able to tell this trend in a group of elements all in the same column. So if you're asked what is the order from smallest to largest for the atomic radius of the elements arsenic, nitrogen, and bismuth, what you would do is locate them in the table. You find they are all group 15 elements, column 15 of the periodic table. So you find the element located at the top and go toward the element located at the bottom. That would tell you that nitrogen, with putting its outermost electron on energy level 2, is smaller in atomic radius than is arsenic, which is putting its outermost electrons in P on energy level 4, which is smaller than bismuth, which is putting its outermost electrons on energy level 6 for a P electron. Now let's take a look at what the trend is for atomic radii as you go across a period from left to right. Remember, a period is a row of the periodic table. Now, elements on the same row of the periodic table are on the same energy level. At least those of the S and the P blocks certainly are. All the electrons in the D block across the period are the same energy level. All the electrons on the F block across the period in the same row of the periodic table are on the same energy level. Now, what this means then is that all electrons at the same energy level are on average the same distance out from the nucleus. So all the P electrons are the same distance out, and so forth. All the S electrons, same distance out, and so forth. But the weirdness comes in the fact that that's not the property that's going to make these atoms bigger. You would think, just guessing, that atoms would get bigger because you're adding more electrons and they're more repulsion, so they're going to get further and further out as you go across a period. But what actually happens is that not only are you adding electrons, you are also adding protons. The protons attract the shell of electrons. The electrons riding on the P ride don't know anything about each other. They have no knowledge of the presence of each other because they're more like waves than particles, and they have destructive interference of their waves, so the waves have no knowledge of each other. So there's no repulsion that they experience towards each other, but there is attraction that they experience to the nucleus. So as you add more nuclear charge, as you go left to right across a period, the effect is to drag the whole shell of electrons on that energy level closer to the nucleus. So the P shell itself shrinks as you go from left to right across the P block on energy level 2. The P block itself shrinks inward as you go across the block on energy level 3, and so forth. So weirdly as it sounds, as you go from left to right across a period or a row of the periodic table, the atoms actually get smaller and smaller and smaller as you go across. The cartoons overlaid on this periodic table are attempting to show essentially both trends. You'll notice that I have red spheres indicating atomic radii. And as you go downward in the various periods, the spheres increase in size, as we've already mentioned. You're adding more energy levels down the group, so the outermost electrons down the group are further and further from the nucleus. But now we're throwing in the fact that as you go from left to right, you're going across the same period, and as you go across the same period, you're adding charge to the nucleus, and the charge to the nucleus is pulling the electron shell entirely in. Even though you're putting more electrons, these electrons are essentially non-interfering electrons, so the entire electron shell gets drug inward as you go from left to right across the table. Now, what's really remarkable about this is, say, as you go from potassium, element 19, over to krypton, element 36. So again, potassium has 19 electrons, krypton has 36 electrons. Yet krypton is tiny, tiny, tiny compared to potassium in size, even though krypton has some 20 more electrons, actually more like 17 more electrons than does potassium. It's the fact that it also has 17 more protons in its nucleus. These protons dramatically shrink the outermost cloud in more dramatically than the added electrons spread the cloud out. So these trends are showing not only do you increase in atomic radius as you go down a group, you decrease in atomic radius as you go across a period. Okay, let's look at doing an example of atomic radii for elements in the same period. Now, again, first of all, before we do this, let me point out to you that when I ask you to do problems like this on your test, they will be elements in either the same group or same period. They won't be diagonal from one another. Like, for instance, if you took the case of oxygen and chlorine, oxygen is further to the left than chlorine, so it should be bigger for that reason. Chlorine is further down the table than oxygen, so it should be bigger for that reason. So there's competing factors as to which of these would be the largest, and I'm not going to ask you for diagonal elements. I'll only ask you if they are in the same row or in the same column. So this particular example asks the question about elements in the same column, and I'm sorry, not column, in the same row. These are the elements O, F, C, and N, which all four are period 2 elements. So to determine their relative atomic radii, you will note that since they're all in the same row, the element furthest to the right is the smallest of the elements. The elements furthest to the left is the largest of these elements, which again might seem a little counterintuitive. But ordering them from smallest to largest, I would say F furthest to the right, smallest element, oxygen next furthest to the right, next smallest, nitrogen is next furthest to the right, and so it's the next smallest, and carbon is the furthest to the left, so it is the largest of these four elements from period 2. Anions are atoms that have gained electrons, and if we then look at trends for anions of the same element, it's pretty straightforward. As you add electrons to an atom, the electrons are added at the valence level. The unfilled shells of electrons are where these incoming electrons have to go. And as you add more electrons to the atom, there are now more electrons than there are protons, so it is net negatively charged, and this additional net negative charge creates a repulsive environment for all electrons. So the more negative an anion becomes, the larger its atomic radius. Now the less negative an anion is, the smaller its atomic radius. Now, what we are speaking about is an anion of the same element. Notice I'm not going to ask you about the relative size of a carbon -2 versus a nitrogen -4. That's not how we're going to do it. I will ask you for anions of the same element. And if the anion is of the same element, then quite simply, the more electrons you add in, the more repulsive those electrons, so the larger that ion becomes. So if you're asked to list the size of the various anions of silicon, neutral silicon would be the smallest, Si-1 would be next smallest, Si-2, -3, -4 would be the largest. And likewise, anions of arsenic, neutral arsenic would be the smallest, arsenic -1 would be bigger than that, -2 bigger than that, -3 bigger than that, -4 bigger than that, and so forth. Again, I wouldn't ask you to compare anions between silicon and arsenic, just anions of the same type of element. Let's contrast the relative size of cations to what we just talked about for anions. First of all, let's remember cations are positively charged atoms, and interestingly, atoms are positively charged not by adding protons to their nucleus, that is energetically daunting to do. Electrons are much less energetically bound than protons. So whenever and wherever we form a cation in nature, in chemistry, we are forming a cation by removing electrons, not by adding protons. As a matter of fact, of course, if you add protons, you're changing the element. That you're changing the atomic number and it's becoming a new element. So in the course of forming a cation, I'm going to remove electrons. So in the course of forming a cation, I'm making a positively charged atom. And when I have this positively charged atom, the remaining electrons, first of all, let's point out, the electron is most likely to be removed from the valence level. Why? They are energetically the most accessible. Now you can remove other electrons than the outermost electrons, but you have to work harder. And typically, once you remove the outermost electron, a valence electron will fall in and take its place when you kick it out. So we will almost invariably then talk about removing electrons at the valence level. And when we remove electrons at the valence level, the remaining valence electrons see more positivity from the nucleus because they're not as much tie up due to the presence of as many electrons as before. So when there is more positive than negative charge, the outermost shell shrinks in. So the more positive you make a cation, the more it shrinks in the outer shell of that cation, so the smaller that cation gets. So if you have cations of the same element, then what you can tell immediately is by the amount of charge on that cation will tell you something about the amount of shrinkage that its outermost shell will experience. Now again, we will not be doing this by comparing, say, an oxygen +2 to a nitrogen +3. We're not going to do anything like that. What we are going to do, though, is compare, say, in this case, manganese cations. So the most highly positive cation of manganese is the smallest. The least positively charged cation of manganese is the largest. And if it's neutral, it's larger yet. And if we were to tack the negatively charged ones on, they would be larger yet. So Mn -1 would be larger than neutral Mn, and Mn -2 would be larger than an Mn -1, and so forth. Likewise with the sequence of aluminum cations, the most highly positively charged aluminum cation, smallest, the least positively charged aluminum cation, or in this case, neutral aluminum atom, largest. Again, we wouldn't try to compare between aluminum and manganese, just within a particular element itself. Let's now describe a very important property as we go towards forming compounds and molecules. That is the so-called ionization energy of an atom. The ionization energy of the atom is the energy required to remove an electron from the ground state of the atom when it is a gas. Okay, now let's make sure we're clear on the words here. It's in the ground state, meaning all the electrons begin in their lowest energy position, but the element is in its gaseous form when we do this measurement. And the reason behind that is we only want to look at the energy required to remove the electron. Remember, if an atom is solid, the first bit of energy you put in it won't remove the electron, it'll change it to a liquid. And then once the material is liquid, the next amount of energy you put in it will change it to a gas. Then finally, when it's in a gas stage, as you add more energy, it'll begin to pull on the electrons on the atom. So some of the energy that you're using here and thinking it's part of the ionization is literally going to change the phase. So we're going to start all the atoms at the same point. That means we're going to start them all from the gaseous position. And we're going to make sure all the electrons are in their lowest energy spots. Then we'll start to measure this ionization energy. Now, the outermost electron of the atom is furthest from the atom itself. And because it's furthest from the atom, it's the least attracted to the nucleus. Now remember, this is weirdly measured. We said it was the highest energy electron. That really means it's the least negative energy electron. Bound electrons are negative in energy, lower than electrons separated from protons to infinity. So the least negative or highest energy electron is least attracted to the nucleus electron. This is the easiest electron to pluck off, and this is the one nature would prefer to pluck off first. So the further the electron is from the nucleus, the lower the energy it will take to pluck the electron loose. So the larger the atomic radius, the lower the ionization energy associated for that electron. So we can tie ionization energy directly to atomic radii. So let's return to our periodic table, and we'll list in red the trends of atomic radii for the elements. Then we'll list in blue the trends for ionization energy of the elements. As you go down a group or down a column of the periodic table, you increase the atomic radius. Outermost electron further from the nucleus. The further from the nucleus, the less attraction to the nucleus. So the further from the nucleus, the easier to pluck away. So as you go down a group of the periodic table, the atomic radii increases and the ionization energy for those elements decrease. Likewise, as you go from, well, not likewise, but in the same manner, as you go from left to right across the period of the periodic table, you are decreasing the atomic radius in the weird sense that we talked about, because you're adding nuclear charge, which pulls the shells of electrons inward. So the atoms actually get smaller and smaller as you go to the right of a row of the periodic table. Since the elements get smaller and smaller, their outermost electron is closer to the nucleus. The outermost electron is therefore tighter bound to the nucleus, and therefore it takes more energy to pluck the electron off as the atomic radius decreases. So ionization energy increases as you go from left to right across the group of the periodic table. Let's look at an example of these periodic trends of the elements and their connection to the ionization energy. So let's list the following elements in order from lowest ionization energy to highest ionization energy. And the elements I'm giving are magnesium, barium, and beryllium. Now this particular slide does not have a periodic table, If you have one handy, you will see these are all group 2 elements. They all reside in column 2 of the periodic table. So they get bigger as you go down the column. And what you will find is beryllium is at the top of the column, magnesium is down below beryllium, and then near the bottom is barium. So, since beryllium is near the top, it has the smallest atomic radius. Since barium is near the bottom, it has the largest. So therefore, the lowest ionization energy is for the largest of the atoms. The highest ionization energy is for the smallest of the atoms. That means barium has a lower ionization energy than magnesium. Magnesium has a lower ionization energy than beryllium. Then we ask for the trend in ionization energy from lowest to highest for the elements chlorine, phosphorus, silicon, and aluminum. These are all period 3 elements, all placing electrons into a 2p orbital. So what we need to figure out is to pluck one of those 2p orbital electrons out. Which of these is the smallest element and which of these is the largest? It'll be easiest to pull electrons loose from the largest. It'll be hardest to pull electrons loose from the smallest. The periodic trend for atomic radius goes from left to right. You go from largest to smallest. So then the ionization energy is opposite. As you go from left to right in the ionic ionization energies, you will increase in ionization energy as you go from left to right. So if you refer to a periodic table, aluminum is the furthest to the left, it's the largest element, has the lowest ionization energy. Chlorine is the furthest to the right, it is the smallest of these elements, and it'll be hardest to pull electrons loose. And so what we find is silicon is next to aluminum, so it is the next highest. Phosphorus is next to silicon, it has the next highest ionization energy. As you might expect, when you're looking at the ionization energy of non-neutral atoms, then the idea that an anion has loosely bound electrons, because they are bigger, even bigger radii, would be easier to pull electrons loose from anions. And for cations, since there are more positive charges than negative charges, you shrink in the electron cloud. So the remaining electrons that are present, you'll have a harder time every time you try to pull an electron loose. And this is exactly what we experience. It is successively harder to remove electrons because the material becomes more cationic. So the more positively charged it becomes harder and harder to remove electrons. So the lowest ionization energy will be for a neutral atom, and the highest ionization energy will be for the most positively charged of that same type of atom. So as we say in this example, neutral chromium has the lowest ionization energy of a series of chromium ions that are increasingly positively charged. Chromium plus 1, the electrons shrink in more, so it's harder to pull an electron loose from it than it is from neutral chromium. Chromium plus 2, even further shrunk in, harder yet to pull electrons loose, and so forth. Now for anions, the more anionic an ion becomes, the more negatively charged it becomes, the bigger it becomes, the further out the electrons get, and the easier it is to pull electrons loose. So an indium minus 4, it would be easiest to ionize compared to an indium minus 3, which would be easier to ionize compared to an indium minus 2, and so forth. Now, once again, in these kinds of trends, I would not ask you to compare between indium minus 2 and lead minus 3 or something of that type. I would only ask you to compare between ions of the same element. Let's talk about the opposite trend or the opposite property to ionization energy, and this is known as electron affinity. So what is the electron affinity? It's the change in energy. It's a little different. It's the change in energy that occurs when you add an electron to an atom. Now, just to keep the playing field level, we're going to add the electron to atoms all in the gaseous state so that they're in the same phase of matter, so none of the energy goes towards that kind of a change in the material. So when I do something like this, I'm going to add the electron to the atom. Of course, I'm going to shove the electron onto the atom at the valence level. I'm not going to be able to shove it into one of the core positions because those are already filled with all the possible electrons they can handle. So the added electron must go on to the valence level. So it's then going to become a function of how far from the nucleus the valence level is as to how well this electron is going to stick. Now, the larger the atomic radius, of course, the further out that valence level will be. So the larger the ionic radius, or the atomic radius of this, or as a matter of fact, ionic radius, the larger the radius of this element, the harder it is to stick an electron. So the larger the atomic radius, the lower that atom has for an affinity to pick up another electron. So smaller atomic radii, higher electron affinities. Larger atomic radii, lower electron affinities. So let's correlate this trend with the layout of the periodic table. Of course, we're going to relate it again to atomic radii listed in red. As you go down a group, the atomic radii increases. So as you go down a group, it's going to be harder and harder to stick an extra electron onto that valence level because it's further out. So as you go down the group, not only does the atomic radius increase, the desire to gain an electron decreases. And as we go across the period, again, weirdly, the atomic radii decrease as you go from left to right because adding more and more protons shrinks in the clouds for the valence level. The valence level gets closer to the nucleus as you go from left to right. So then the valence level is closer, an incoming electron can stick better, and so you will lower, you will be lowering the atomic radius, and you will be increasing the ability to stick an electron on to that nucleus. So as the atomic radius decreases, the electron affinity increases. So as you go across a period, you're going to increase the electron affinity. So let's look at a couple of examples of this property. List the following elements in order from lowest to highest electron affinity. And I give you the elements hafnium, titanium, and zirconium. They are in the same group. They happen to be D block elements. They are all in group 4 of D block. I'm sorry, I don't have the periodic table sitting right here in front of you, but they're all group 4 D block elements. And so what that would mean is the element near the top will be the smallest of them. The element near the bottom will be the largest of them. So if you are a large element, you have a small electron affinity or low electron affinity. If you are a small element, you have a large electron affinity. So down this particular group, since hafnium is the largest element in the group, it has the lowest electron affinity. Since titanium is the smallest element in group 4, it has the highest ability to gain an electron, and zirconium is somewhere in between those two. Okay, then let's list the elements shown below in terms of their electron affinity when they're selenium, gallium, arsenic, and bromine. These are all period 4 elements, not group 4, period 4. They're across the 4th row of the periodic table. As a matter of fact, they're all putting electrons into a level 3p orbital being in group 4. In period 4. So, once again, the smaller the element is, the better affinity it will have to add in an electron. The larger the element is, the harder it will be for it to add an electron. Gallium is the furthest to the left. It's the largest of these elements and has the lowest ability to gain a new electron. Bromine is furthest to the right. It is the smallest of these elements. It has the best ability to gain an electron. And then arsenic, which is a column 15 element, and selenium, column 16 element, are in between. So the order goes gallium, lowest electron affinity because it's largest atom, followed by arsenic, selenium, and then bromine has the highest electron affinity because it's the smallest atomic radius of these 4 elements. The electron affinity trends for ions are probably pretty much what you would expect them to be. And again, this is the desire to gain electrons. So again, the smaller the ion, the closer in an incoming electron can get to the nucleus, and the more affinity that ion has for picking up an extra electron. So the more positively charged a cation, the smaller the atom becomes, and therefore the better it has an ability to gain an electron, so therefore the higher the electron affinity. So for these positively charged types of osmium, the neutral osmium has the lowest electron affinity, and going up to the positive 4 osmium, that will have the highest electron affinity. Now, as you can imagine, the trend is opposite for anions. The more negatively charged you are, the bigger your ionic radius. The bigger your ionic radius, the further out your valence level. The further out your valence level, the lower your electron affinity. So the most negatively charged gallium will have the lowest electron affinity. The least negatively charged gallium will have the highest electron affinity, and then those in between will have sequentially increasing values of electron affinity.